What I want to do here is calculate the inductance in a coil. This is a theoretical calculation. This is not doing it just by measuring the time constant or something like that with the practical gear. So a few things we need to have a little think about to do this. Let's look at Faraday's formula, which was to do with delta flux over delta T. We won't forget the negative, but we also can put a n in there for the number of turns, because the flux is per turn. And what we could say is that the actual amount of, because what we're trying to get to is this inductance thing. What we could say is that the actual reason this flux here is changing is because the current through the coil is changing, and that current produces a magnetic field. In a coil it's going to produce a magnetic field down the center. That magnetic field in that area is a flux, and it will change as the current changes. So what we're looking for is something that's going to give us this L di dt, and we'll call that L thing inductance. Now what I want to do is physically work out what that is for a particular coil, and this L is going to be a constant thing, just like capacitance. For a given construction, it's going to have a value. If we look at this I'm going to do some things now that I'm not going to prove, but in calculus we wouldn't just do it like this, or maybe we would. We'll just cancel out the dt's, and what we can end up doing is saying that n di equals L di, and actually we can end up saying n flux equals Li, or L equals n flux over current. Quite a brave statement to make, and I haven't proved it, but based on that, if we base it on that, then, and thinking, hey, maybe that's about right, calculating the inductance theoretically, then maybe we can use that to work it all out. Now, you probably remember that in year 11 you had a formula for the magnetic field around a wire. Distance from a wire, magnetic field. You won't probably have had this formula, which I don't know why. It's actually a simpler formula, which is that the magnetic field in a solenoid, electrical coil, is that. Gives you the strength of the magnetic field. Now the little n is number of turns per meter. N equals number of turns per meter. So we could use that. So little n, we could say, is actually equal to a big N divided by L, length. Right? So now we're starting to get, why am I doing this? Because I'm looking to see if I can get a formula for the flux. If I can do that, I'm on my way to maybe working out theoretically the inductance in a coil. So we've got a B, and all we need to do is multiply that by an area, and we've got a flux, right? So then we're just about there, really. So mu naught little n, I'll put the big N back if you like, which means we have to put it over L times I, that's the flux, times the area, that's flux. We have to multiply that by another n, don't we, because we got that, and I is underneath there, and that's what L equals. So we can actually cancel out the i's, so the L is not related to the current going through it, so we're already starting to see that it actually is just related physically to the coil. So we can say that it actually equals mu naught big N squared A over L. Now if we make some substitutions, and the substitutions we can make is that big N equals NL, so let's do that, mu naught, and n squared then equals big N squared equals little n squared L squared A over L. We can cancel that, and we've got u naught little n squared LA. So actually what we found is that if we call that the volume of the coil, the inductance on the coil equals mu naught little n squared times the volume of the coil. Nice, simple little formula. Beautiful.